In the version of the Cauchy integral formula that we have proved, we have imposed a strict condition on the curve in question. We demanded that the curve be homotopic in C minus Z naught to a circle of radius r around Z naught for some r positive. Now that's a pretty stringent condition to impose on the curve gamma, and we would like to circumvent this condition, and the route to getting a more general Cauchy integral formula is by introducing the notion of a winding number. Let us begin this week by defining what the winding number of a curve gamma around a point Z naught is. So let's start by defining winding number. So to do that, let gamma be a closed curve in the complex plane. So it's a closed continuous curve on the complex plane, and let z0 be some point which is not on the image of gamma. Image of gamma. We define the winding number of gamma around Z naught to be the following integral, which will denote as W gamma of Z naught. This is defined to be 1 by 2 pi I times the integral over gamma dz by Z minus Z naught. Notice that 1 by Z minus Z naught is defined away from Z naught, and the fact that Z naught does not belong to the image of gamma gives sense to what we have just defined. So let me underline what we have just defined. We have just defined the winding number of gamma around Z naught. Let's look at a couple of examples. When gamma is, say, from 0 to pi to c given by gamma of t is equal to z0 plus e to the power 2 e to the power it. Suppose we have such a curve, then clearly z0 does not belong to the image of gamma. After all, gamma is the circle of radius. Let's put an r here, some radius r for some r positive. And we know that W gamma of Z naught will just turn out to be equal to 1 by the Cauchy integral formula. And if gamma is in particular, again, gamma of t is equal to Z0 plus r e to the power I mt for t in 0 to 2 pi. Then if you look at W gamma, or maybe I'll call it 0 and 1 here, then if you look at W gamma 1 of Z naught, should sit down and check that that's going to be equal to m. Let's now draw pictures and check what was happening. We have our complex plane, and we have some point Z naught, and let's look at the circle of radius r around Z naught. If you notice the circle of radius r around Z naught, it goes around the circle exactly once and comes back to the initial point. And if you look at the second case where gamma 1 is z0 plus r e to the power 2 I m t, what does it do? It goes around the circle. When t is 2 pi by m, it comes back to the starting point. It goes back again along the same circle, and it keeps winding around the point m times. The winding number W gamma Z naught exactly captures this particular notion. It captures the number of times a particular curve is winding around a given point. As is to be expected, the winding number is being the number of times it winds around a point. It should be an integer. But we will come to that only in the later part of this lecture. Initially, let's explore some of the nice properties of winding numbers that we can easily conclude. So for example, let gamma 0 and gamma 1 be closed curves, such that in C minus Z naught, such that gamma 0 is homotopic as closed curves to a reparameterization of gamma 1. So that gamma 0 is homotopic as closed curves to a reparameterization of gamma 1. So that basically means where in C minus Z naught. That basically means that Z naught is not in the image of the homotopy that is there. That's what it means, right? Then what do we know about dz by z minus z naught over gamma 1? We know that by the Cauchy's theorem, this is going to be equal to integral over gamma 2 dz by maybe gamma 0 and gamma 1, right? This is going to be equal to the integral of z dz by z minus z naught over gamma 1. In C minus Z naught, 1 by Z minus Z naught is a holomorphic function. So in particular, the integral of this function along any two homotopic curves is going to be the same. In particular, by introducing a 1 by 2 pi I term here, we get to conclude that the winding number of Z0, gamma 0 around Z naught, this is the same as the winding number of gamma 1 around Z naught. So the conclusion is here that two homotopic curves which are homotopic as closed curves, they are going to wind around a given point Z naught the same number of times. The fact that the winding number is invariant under homotopy will be used very crucially by us. We will move freely within a homotopy class from one curve to other in order to calculate the winding number. Many times it happens that a homotopic curve is where it's easier to compute the winding number, and we will freely shift to that. One more point I would like to notice is the following. The winding number that we defined is just for arbitrary continuous closed curves. And if you recall the definition of the integral of a holomorphic function on an arbitrary closed curve, what we did was to get hold of a polygonal path which was homotopic to this continuous curve and defined the integral to be the same as the integral on the polygonal path which is homotopic to it. And we use the Cauchy's theorem, the power of the Cauchy's theorem, to say that this definition is indeed a valid definition. And something similar is what will be done here to talk about winding numbers. We will freely move in the homotopic class, pick the particular curve which is the most suitable to work with, and then try to prove our results. Let's look at one more consequence of this invariance of homotopy. Let's call it a proposition. Suppose we have a curve gamma. Let maybe gamma 0 be a curve from AB to C, be a closed curve, and Z0 be a point not in the image of gamma 0. Not in gamma 0. Let me do an abuse of notation and just say that it is not in gamma 0. Suppose gamma 1 from AB to C be a closed curve such that absolute value of gamma 0 of t minus gamma 1 of t, this is say strictly less than the absolute value of gamma 0 of t to z naught. Then the conclusion is the following: and the winding number of gamma 0 around z naught is the same as the winding number of gamma 1 around z naught. Notice that the inequality that is written here ensures that z0 is not going to be a point in the image of gamma 1 either. In order to prove this theorem, what will be done is to establish that gamma 0 is in some sense homotopic to gamma 1 in C minus z naught. Let's in fact explicitly write down what the homotopy is. Define the function h from 0, 1 cross AB to C minus Z naught. So let me not write minus Z naught as of now. There is something to be done to check that it is indeed missing the point Z naught. Let me just define h of s comma t to be at stage s. This is 1 minus s times gamma 0 of t plus s times gamma 1 of t. Notice that this is going to be a continuous function into C, and that h at every stage gives us a gamma s, which is a closed curve. H of 0 comma t is equal to gamma 0 of t, h of 1 comma t is equal to gamma 1 of t. So in particular, this is indeed a continuous map, which is a homotopy from gamma 0 to gamma 1. The only thing to note is that we still have not checked that z0 does not come in the image of h. So the claim is that z0 does not belong to h of 0, 1 cross AB. Let's see what can be done. We will try to see what is h of s comma t minus z0. Let's write that down. What is the absolute value of this? This is going to be equal to 1 minus s times gamma 0 of t plus s times gamma 1 of t minus z naught. This is what we are computing, right? Let's add and subtract a gamma 0, and if we do that, what will we get? We will get, by subtracting a gamma 0, we will get s times gamma 1 of t minus gamma 0 of t, and by adding a gamma 0, we get gamma 0 of t minus z naught. Now let's use a triangle inequality, a variant rather, and we will be able to write this as greater than or equal to gamma 0 of t minus z naught minus s times absolute value of gamma 1 of t minus gamma 0 of t. And if you notice, this is again greater than or equal to absolute value of gamma 0 of t minus z naught minus absolute value of gamma 1 of t minus gamma 0 of t. Let me now take you to the hypothesis of this proposition. Our assumption was that absolute value of gamma 0 of t minus z0 minus the absolute value of gamma 0 of t minus gamma 1 of t is a strictly positive number. So this is going to be strictly greater than 0. And if you go up, we just ensured that h of s comma t can never be equal to z0. And hence, h of s comma t is not equal to z0 for any s comma t in 0, 1 cross AB. That means that h is a homotopy in C minus z naught, homotopy of closed curves in C minus z naught from gamma 0 to gamma 1. And that implies that the winding number of gamma 0 around z naught, this is the same as the winding number of gamma 1 around z naught. And that's precisely what we were trying to show. So if our curves gamma 0 and gamma 1 satisfy this inequality, their winding number around z naught is going to be the same. Let's now try to see what happens when z0 is a point which is close to infinity, whose absolute value is large. Let's try to see what would be the winding number of a curve around such a point. We just developed all the necessary prerequisites to answer this question. So to do that, let gamma be some curve, be a closed curve, and z0 be a point in the complex plane such that the distance of gamma to z0 this is greater than the diameter of gamma. Let me define what these objects are. The distance of gamma to z0, as is to be expected, it is the distance of the point z0 to gamma, which means that it is the distance of the infimum of the distances of all gamma of t comma z0. The distance here is just the absolute difference of the absolute value of the difference, where t belongs to AB. This is precisely what the distance of gamma z0 to gamma is. And what about the diameter of gamma? That has already been defined earlier. That's defined to be the supremum over all t and t prime in AB, the distance of gamma of t and gamma of t prime. Right. So our assumption here is that the diameter is less than the distance of z0 to gamma. What happens when we have such a scenario? Let's define a new curve. Define gamma 1 of t to be equal to some point z, or rather the fixed point z, which is equal to gamma of a, the starting initial point of gamma. Let's define a new curve gamma, which is the constant curve at the point z. And if you notice, absolute value of gamma of t minus gamma 1 of t, this is bounded by the diameter of gamma. And what was the diameter of gamma? Like diameter of gamma is bounded above by the distance of z0 to the curve gamma. Distance is the infimum, so in particular this is less than or equal to the absolute value of gamma of t minus z0. Now we are in the situation of this proposition. We have just obtained such an inequality, and therefore the winding number of gamma 0 around, or rather gamma around z0, this is the same as the winding number of gamma 1 around z0. But what is gamma 1? Gamma 1 is just the constant curve at z0, and therefore this is just going to be equal to 0. So when the absolute value of z0 is very large, say, so suppose this is our curve gamma, and we take some point z0 very far away from this particular curve, what it tells us is that the curve does not wind around z0 as is to be expected. Let's next show that the winding number is in fact a locally constant number. So let me write that down as a proposition. Let gamma be a closed curve and z0 be a point not in omega, not in gamma. Z0 be a point not in the image of gamma. Let me just write it as not in gamma. Then there exists an R positive such that on, or rather for z in dz0r, w gamma of z is equal to w gamma of z0. That means it's a locally constant function. Let's try to give a proof of this. Now, since image of gamma is a compact set, in particular it's a closed set, and since z0 does not belong to the image of gamma, it's going to be in the complement, which is an open set. So there is certainly an R, it's an interior point. So let me write down all that I just said. There is going to be an R such that dz0r does not intersect the image of gamma. Since gamma of AB is closed and z0 does not belong to gamma of AB, there exists R greater than 0 such that dz0r intersected with gamma of AB is empty. Now let's pick some point H in the complex plane. Let H be in C such that absolute value of H is less than R. And let's look at the following curve. Define gamma H of T to be equal to gamma of T minus H for T in AB. Let's see what happens when we look at gamma H here. What is going to be the absolute value of gamma H of T minus gamma of T, or the other way? What is the absolute value of gamma of T minus gamma H of T? It's going to be equal to the absolute value of H, which is strictly less than R, which in particular, let's see what is R. R is positive number such that dz0R intersected with gamma AB is empty. In particular, the distance of gamma to z0, or rather distance of z0 to gamma is at least R. In particular, if you look at the difference gamma of T minus z0, that has to be greater than R, right? And now we are in the setup of our proposition, which tells us W gamma H of Z0 is equal to W gamma of Z0. I'm going to give you an exercise to check that what is W gamma H of Z0. By definition, this is equal to the integral 1 by 2 pi I times the integral over gamma H dz by Z minus Z0. Now this is going to be equal to 1 by 2 pi I integral dz by, recall that gamma H of T is gamma of T minus H. So this is going to be Z minus Z0 plus H over gamma. This is the exercise that is expected. Now if gamma is a smooth curve, or even a piecewise smooth curve, by a change of variable, it's very easy to check whatever we have written here as an exercise. So let me just write it down as an exercise for you. By the way, this on the right is just the winding number of gamma around the point z0 plus h. Notice that z0 plus h is going to be in the disk of radius r around z0, and hence it does not belong to, the point does not belong to the image of gamma, and therefore the winding number makes sense. The only thing to be checked is this particular equality for the general case. In order to do that, what is to be done is that you pick a partition of AB with partition size small enough so that not only is the polygonal path that you get by connecting the nodes homotopic to our curve gamma, but also its translation will also be homotopic to gamma h. And through that, you will be able to establish this particular equality. And therefore, we will be able to conclude that the winding number of, notice that we already have this, that the winding number of gamma h around Z0 is the same as winding number of gamma around Z0. And from star, let me write this as star, from star we have the winding number of gamma around Z0 is the same as the winding number of gamma around Z0 plus h. And that's precisely what we were trying to prove for h, such that mod h is less than r. This is true, and therefore hence winding number is a constant on dz0r. Now that we have explored some nice properties of winding number, let's get to proving that the winding number is always going to be an integer. Let me note that down as a theorem. Let gamma be a curve in the complex plane and be a closed curve rather. And z0 be a point not in gamma, not in the image of gamma. then the theorem states the following: W gamma of Z naught is an integer. Okay, let's give a proof. The first thing to note is that even though we have put continuous closed curves in the generality of continuous closed curves, the first observation is that we don't need to worry about that level of generality. We just need to focus on a polygonal path which is homotopic to it. So let me first note that by picking a partition P, which is say A equal to T1 less than T2 less than up to say Tn equal to B, such that gamma restricted to Ti or rather Tj plus 1 is homotopic with fixed endpoints. To what? To gamma Zj to Zj plus 1. Suppose this straight line path where Zj is just equal to gamma of Tj. So suppose we start off with a closed curve and suppose the point Z0 is here, then let me use red color to get hold of a partition, something like this. And we call this Z1, Z2 all the way up to Zn minus 1, and then this is Zn. So we look at the polygonal path which is obtained by connecting these points. And then, so where is this homotopic? Homotopic in C minus Z naught. It's important where it is homotopic. Then in particular, gamma is homotopic to gamma Z1 to Z2 to Zn to Z1. This is a closed polygonal path. And therefore, because it's homotopic and since at every stage the curves here are homotopic, we can use that homotopy to construct a homotopy from gamma to this polygonal path as closed curves. I will leave that as an exercise for you to sit down and check. The idea is that we now have the winding number of gamma is the same as the winding number of this polygonal path. So we may as well have started off with this polygonal path itself. So since the winding number of gamma around Z0 is the same as winding number of gamma Z1 all the way up to Zn to Z1 of Z0, we may start with the assumption that gamma is a closed polygonal path. So for the purpose of this proof, we will assume that gamma is a closed polygonal path, and we will now try to prove that the winding number of such a closed polygonal path around a point Z0 is a constant. We will prove this by induction. Let us now prove the result by induction. So to do that, let's first draw the picture and we will write down the induction hypothesis after that. So we have a polygonal path. Let me first draw the polygonal path. So we have a Z1, Z2 going on. This will be Zn minus 1. This is going to be Zn and back to Z1. Now let's look at the line joining Z1 to Zn minus 1. So the first observation is the following. Suppose So we know that z0 does not belong to the image of this curve, but suppose z0 belongs to the straight line joining gamma zn minus 1 to z1. Then the first observation is that because since our winding number is going to be equal to any other curve z for z in dz0 r, where r is as in the proposition earlier, where r as above in the previous proposition. Because of that, what we can do is we will be able to pick some point z prime, say, which is not on the line joining z1 to zn minus 1. Pick a point z prime which is in dz0 r, and z prime does not belong to the gamma zn minus 1 to z1. So we have ensured that we are picking some point somewhere here or somewhere here. That's what we have just ensured. We are ensuring that that particular point is not on this straight line. Let us now apply the induction hypothesis on the number of points in the closed polygonal path. Induction is on the number of points. On gamma, on the number of points z1 to zn. That's what the induction is on. Assume that it's known for up to n minus 1. So suppose for n is equal to 0, n is equal to 1 and n is equal to 2, it's a trivial case and we don't have to address that case at all because we don't have non-null homotopic closed curve. When n is equal to 3, what do we have? Let's see what happens when n is equal to 3. Then we have a triangle and our z0 is going to be either in the exterior or in the interior. What does that mean? In the convex hull, in the interior of the convex hull, or it is in the exterior, in the complement of the convex hull. In either case, what do we know? If z0 belongs to, let me call the triangle T hat interior, then the Cauchy integral formula by Cauchy integral formula 1 by 2 pi I integral dz by z minus z0 is just going to be equal to 1 when integrated over gamma. So this is when z0 is the red case. And what happens when z0 is in the complement? C minus this. Then our triangle is null homotopic in C minus z0, and therefore 1 by 2 pi I integral over gamma dz by Cauchy's theorem, this is going to be equal to 0. And in either case, our winding number is going to be either 0 or 1, which is an integer. Hence, W gamma of z0 is an integer. Now assume that the result has been proved for up to n minus 1. Assume the result to be proved for up to n minus 1. Then what do we have? Then W gamma of z prime, in this case, what can we write this as? This is going to be equal to, let me just write it down and then we'll look into it again. This is going to be z1 to zn minus 1 to z1 of z0 plus W gamma z1 to zn minus 1 to zn to z1 of z0. This is just splitting the two integrals. This is 1 by 2 pi I integral over this curve of dz by z minus z prime. Let me be a little careful. This was not z0. We picked our z prime in such a manner that it will not be on the line joining zn minus 1 to z1. And The second term here will be 1 by 2 pi I integral dz by z minus z prime over the curve, which is the triangle with endpoints z1, zn minus 1, zn. And if you notice, what we have done is we split this integral as one in this direction and the green one is the triangle. And if you notice, the green and the black on this particular straight line will cancel each other off. What we get would be the integral over the closed polygonal path. So getting back to what we have here, by induction hypothesis, this is an integer. And for n is equal to 3 case, we already saw that this is an integer. And therefore, hence W gamma of Z prime is an integer. And this tells us that W gamma of Z naught is also an integer. It's after all locally constant function. So in fact, we have established that the winding number which is being captured by gamma is indeed an integer, and intuitively it's the number of times or the number of winds that the curve has around a given point z naught. Okay, we are now in a good situation to give the more general Cauchy integral formula without the imposition of an extra condition of our curve gamma being homotopic to a circle of radius r around z naught. Let me write that down. So let f be a function holomorphic on omega on an open set. And gamma from AB to omega be a closed curve which is null homotopic. Recall that null homotopic means that the curve is homotopic as a closed curve in omega to a constant curve. Then for z0, which is not in the image of gamma, we have f of z0 times the winding number of gamma around z naught. This is equal to 1 by 2 pi I integral over gamma f of z by z minus z naught. Let's give a quick proof of this. We have done all the hard work already. The general Cauchy integral formula now follows by a few observations. The first one being that if you look at the function f of z minus f of z naught, this is a function which has a 0, it vanishes at z naught, it has a 0 at z naught, and therefore by the factorization theorem, what did the factorization theorem say? If f is a function which vanishes at z naught, then f can be written as z minus z naught times g of z. For holomorphic functions, we can write this as z minus z naught times g of z, and hence on omega we have f of z minus f of z naught by, or rather, and hence if you look at the integral over gamma of f of z minus z naught, this is the same as the integral of g of z. Notice that z naught is not in the image of gamma. So, this is in fact even otherwise it would have made sense. The point is that this is the same as the integral of g of z over gamma, and being null homotopic by Cauchy's theorem, this is equal to 0. This is by Cauchy's theorem. And therefore, what we get to conclude here is that 1 by 2 pi I times the integral over gamma of f of z by z minus z naught. This is equal to the integral of f of z naught by z minus z naught dz. And the right hand side is exactly equal to f of z naught times 1 by 2 pi I into integral of dz by z minus z naught over gamma, which is the winding number of gamma over z naught. And that's precisely what we are trying to prove. Okay, let me stop here.